after that if you have any questions. No. Okay.
Thanks for explaining. Go into detail. Really cool. Thank you.
So, I mentioned that we do tracking of juice and wine. So we'll receive grapes during harvest, and they get crushed at the crush pad, and they get put into tanks, which we call fermenters, and then we start tracking fermentation. And so basically where we start is by measuring the amount of sugar in the juice as it's fermenting into alcohol. And so we'll take like an initial measurement of the sugar of the juice before we inoculate it with yeast. And then we track it every day. And once the sugar gets below a certain point, we change our method of measurement. So during fermentation, we'll track it with, I'll show you the instrument. It's pretty rudimentary, but it's robust. So this is called a densitometer, and it gives us the measurement called brix, which is essentially sugar. It's technically solubilized solids, which is mainly comprised of sugar. And so we will take a sample. Let's call this, pretend this is grape juice. And we just suck it up into the tube, and then it gives us a measurement. This is water, so it should be 0 or really close to 0. But if we were measuring juice that we had just received, then it would be closer to like 25 brix.
So you want your wine to have like the 25 brix?
Typically, juice that's going to be fermented needs to be around 25. You can think of alcohol, you can think of the final alcohol as being about half of what the initial brix reading is going to be. So if you're starting with 25 brix, you're going to end with somewhere around 12% alcohol.
And then is the temperature on there, you want a certain temperature for the wine, or?
While we're fermenting, we want the temperature to be below 80 typically. Below 80? Yeah, the temperature is really important. For whites, we keep it even cooler, and that will lengthen the duration of the fermentation. As you raise the temperature, the fermentation gets a little bit more excited, happens a little bit faster. Hey Drew, how's it going? Good, how are you? No, she came in. Oh, okay. Yeah, so yeah, we try to keep the temperature between a certain range. It's usually between 70 to 80 degrees Fahrenheit. Anything more than that, and the yeast will get too hot and potentially die, and anything cooler than that, and the yeast will get really sluggish, and the fermentation won't actually, it'll just take forever. So then once the brix drop below 0, we'll use this instrument to measure the sugar. This is an enzymatic reactor. It's actually refurbished. These instruments were built to work in hospitals to measure different chemicals in blood and urine. And there's a company that pulls them out of the hospitals, refurbishes them, and kind of modifies them for the wine industry. And so with this, we're able to measure what we call RS, or residual sugar, which is a combination of fructose and glucose. And then we can also measure malic acid, lactic acid, acetic acid, God, what else? Citric acid, all kinds of things.
Yeah.
So these are all, again, quality markers. So we want to keep an eye on residual sugar, even as the fermentation's finishing up and all of the sugar's been converted into alcohol. We'll still monitor it to make sure that as we're kind of adjusting the wine and blending it, that it's fitting within our final target for that particular product.
And if it doesn't fit that final product, then you just switch in, like how
Well,
used.
if it's like above or below, we have lots of time to really
Alter.
make sure that it's, to get it in target. But again, it's one of those things where, if we're adding another wine, one volume of wine to another volume, and one volume has significantly more sugar in it than the other, we need to make sure that all of our calculations are correct and that we hit our target. And typically we do. We're pretty good about that. It's not just like, let's just add some more sugar, let's just add some wine. Like, it's all very structured.
Yeah, calculation.
Yeah. So, but this just enables us to assure that we're meeting those quality markers. And basically, this is this has got 72 different individual cuvettes that are essentially reaction cups, and then in this, so we have reagents here, as well as cleaning solutions. Doesn't like it when you open that. Well, it's cleaning right now. And so basically, the little probes will go in, and it's all automated, and it pulls up the reagent or it pulls up the cleaning solution, mixes it in the cuvette, and then there's a spectrometer there that that we use to measure. So, and then it all is calculated for us, and we get what the readout. Let's see here. So we get the measurement provided to us in grams per deciliter, grams per 100 liters, or 100. And so, we don't have to do any calculations. It just kind of spits out the results for us. Yeah, and the different chemicals, like this is malic acid, which is converted. Well, it's a second fermentation, and what happens is we have lactic acid that converts into malic acid, and in the winemaking process, what that essentially does is it makes the wine more palatable. Before malic acid takes place, the wine can be really acidic and tart, and so when it goes through malic acid fermentation, it kind of rounds it out and makes it kind of creamier and smoother. And so almost all wine, red and white, goes through secondary fermentation, malic fermentation.
So is that like balancing pHs to make it less acidic?
We do that too, but the pKa of malic and lactic acid are such that it's not going to have a huge effect on the pH of the wine. But it does have an effect on the perceived tartness. Yeah. The main contributor to pH of a wine is tartaric acid. That's what exists in the highest concentration out of all of the different acids in the wine. Tartaric is the most abundant, and I'll talk about that in a minute. But that's a huge aspect of wine quality. So this is an enzymatic reactor with a spectrometer. This is a micro GC. It's not a common brand actually. It's Falcon, which is made on the East Coast, U.S. made. It's been basically designed essentially for petroleum, but they've modified it and tried to tailor it for the wine industry as well. Mm-hmm. And so we've had a few issues because in petroleum they do a gas injection and we do a liquid injection. So we're still kind of messing. It's still kind of in beta phase. But essentially what this does is measures ethanol. And the GC is kind of the preferred method for measuring ethanol in the wine industry, because you don't run into interference when you have carbonation and sugar, where if you're using an IR, those molecules will interfere with your measurement. So this is really a great kind of clean, straightforward method to measure ethanol in fermenting wines, where you have a lot of carbonation and sugar.
Yeah. So all these are testing little things of wine, or all separate pieces of the wine, like.
Well, so the wine samples that we're testing all pretty much look the same. Like, it's either fermenting juice, some point through the fermenting process, or it's finished wine. And with all of these instruments, it's actually quite beautiful. We don't have to do a lot of sample prep other than using like a centrifuge to spin down the solids and remove the, and then we decant the wine off of whatever solid might be in the sample. But essentially, so for instance, like this is our control, or what's left of this container of it. But it's just wine. It's just.
So that tests the ethanol out of that wine, and then that tests the acidic.
This tests the sugar, and VA is what we refer to as volatile acid, which is essentially acetic acid, and it's a byproduct of microbial contamination and oxidation. So that's another quality marker that we can measure with this. But it's just wine. That's it.
So once it's all tested, it could be like drinkable, or decide if it's of the right value.
Well, so you mean like the
ethanol is like the right amount you want, and then acid, and it's like in the stores.
Well, so we're testing the wine throughout the processing of it. So, once we finish fermentation, we'll age the wine, so it sits around for a couple months, and then we will fine the wine, and there's all kinds of different ways to fine it, but basically fining refers to either clarification, or we'll add products that will kind of smooth it out, like if there's some really harsh tannins, which can make a wine kind of give it like a chewiness almost, or an astringency. We can add things to it that will kind of mitigate those characteristics, soften it, make it more close to what our target consumer is looking for in a specific product. And so there's all these different processes, filtration and fining and aging, and maybe we'll do an acid adjustment or sugar adjustment, and all of that can take place over the period of maybe 8 months to several years, depending on what kind of wine we're talking about. So we're checking all of these different chemical markers throughout all the processing steps. And then as the wine gets closer to bottling, we'll do yet a few more checks, bottle it, and then it's ready to drink. In theory, the wine is drinkable throughout most of the processing steps, but it's just not something you would want to drink.
Yeah,
it's not clear, it's not quite balanced, and with the volume that we make here, we do a lot of different products with what we call legs. So if we're dealing with a product that maybe we're going to bottle 100,000 gallons, well, we're not necessarily going to keep all of those gallons in one tank. We're going to have multiple smaller tanks, and each of those smaller tanks are like components of the final blend. And so one tank might be really oaky, and one tank might be a little bit sweeter, and one tank might have a different kind of aromatic profile or something. And so on their own, they're not really something you would consider drinkable, but once they're all combined, they really all contribute to the final blend and the product that's on target. So that's sort of the general process. And so we're testing, with any time we add something, a blend or whatever, we're going to use different instruments to test the wine to make sure that whatever that processing step was, it achieved the goal, right? So this guy we used to test ethanol during mid-fermentation, and the reason we do that is because depending on the alcohol content of the wine, there's different tax levels determined by this regulatory body called the TTB. And so if a wine is below 14% alcohol, then it's in like a certain tax bracket, and if it's above, then it's in a higher tax bracket. And so we need to make sure that by the time the wine's done fermenting, we know what amount of alcohol it's going to be, so that we can allocate the proper funds to make sure that we have the right, that we can pay the taxes on it, essentially. And so we run what are called mid-alcs. So mid-fermentation, we'll run a sample, and we run the ethanol, and then we also run the RS, and we can combine that number basically to get a projection of what the final alcohol will be. And essentially we're just taking the RS and dividing it in half and adding it to whatever the current alcohol or ethanol reading is, and that's going to give us our final ethanol amount. So this thing's pretty snazzy when it is working. It's very fast. It doesn't have an oven to heat a column, so I don't know if you guys have ever worked with a GC, gas chromatography. No, you don't have one of those in your lab? Oh, okay. Well, in college you'll definitely work with that. It's pretty, it's a pretty common instrument to have. And essentially what you're doing is injecting a sample into this port here, and based on the mass to charge ratio, the molecules in the sample kind of spread out through the column and are separated and then kind of flung onto a detector individually. And so the detector can tell you the concentration of each different kind of molecule that you have in your sample. And we just have a basic flame detector. It's not a mass spec where you can do like molecular identification. This is really just sort of dialed in to identify one type of molecule based on where it's and what's the word I'm looking for? I want to say ejected, but based on the time that it hits the detector. So we're able to kind of dial that in and say, okay, we're expecting ethanol to be emitted at this time, and we can hone in on that and really get a really clear view of how much is in the sample. And it's really amazing. This is the syringe that draws up the samples from these they're little 1.5 ml vials, and this is a 500 nanoliter syringe.
Oh, wow.
So the sample is really like a fraction of a drop that gets injected.
Oh, wow.
It's very, very, very tiny. And then again, this doesn't have an oven like a normal GC. It's heated inductively. So it heats immediately and basically turns the sample into, volatilizes it so that it can move through the column. And that's really helpful because we don't need a lot of sample, and it moves much faster than a traditional GC. So this is another fun instrument that you'll probably get to play with in Gen Chem one day. This is an FTIR. FTIR stands for Fourier Transfer Infrared Spectrometer. And Fourier Transfer, that's just, it's a term for the calculation that converts the reading into an actual number that makes sense. Like, we're talking converting wave numbers into concentration, essentially. And this is a great instrument because, again, we don't have a lot of sample prep. We can just pour the wine into these little vials here, load this tray up, and this is an auto sampler. So basically, we program the auto sampler on the computer and fill it up with the samples, and it just runs everything for us. We're not having to sit here manually, dunking the sample needle into each sample and doing it all. It's all, program it and walk away. Well, I wish it was that simple. This thing's actually very temperamental. It runs with a series. Well, there's a laser in it, and the laser is positioned with a series of mirrors, and so any kind of disruption, vibration, anything that happens in the environment can throw this thing off just a little bit, and it won't want to function properly. So it is actually quite temperamental, being that it's a pretty straightforward instrument in terms of the manual operation and maintenance. There's not a lot to it. All of the cool stuff happens in the back there, but I wouldn't dare. Not gonna. I already got it all dialed in. I'm not gonna mess with it. This is an instrument that's really specific to the wine and beer industry. It's called an alkalizer, and it uses NIR, near-infrared spectrometry, to measure alcohol in a sample, and it's great for still wine that's completed fermentation, but when you have wine that's in mid-fermentation that has CO2 and sugar in it, the spectrometer will experience interference because the carbonation and the sugar molecules are quite large, and they just kind of disrupt the ability for the instrument to read the sample. So it's not great for fermenting samples, but it's perfect for still wine samples, which is what you see around here. And then we have a densitometer that gives us our specific gravity, our density, and the Brix reading again, which is the sugar reading, which is going to be below 0 for a still wine. It's actually a calculated value using the density, and I'm not actually sure of the formula right off the top, but so when a wine sugar is below 0, the Brix you can get like negative 1.3 or negative numbers.
Yeah.
They don't necessarily make a lot of sense in terms of the sugar in the wine, other than it's telling you that it's dry and there's very little of it. That's why we also like to use the RS, the residual sugar measurement, because that actually tells us the amount of sugar in the wine. So there's a little bit of difference, but they're basically the same number. They're just used differently. This is an orbisphere, and basically what this does is measures O2, oxygen, and CO2, carbonation in the wine. And those are very important things to keep track of, because with all of the processing that we do with our wine, whether we're adding something to it and mixing it up, or blending wines and combining them, those are all basically opportunities for the wine to pick up oxygen. And that's a bad thing, because oxygen can lead to oxidation of a wine, which is like aging of a wine. And so that's like no bueno. So we try to minimize the amount of oxygen that a wine can pick up. And if we do something like truck some wine in and pump it out of the truck and into a tank, we're going to expect the oxygen levels to be pretty high, because that's pretty rough treatment of the wine, and there's lots of opportunities for it to pick up oxygen. So we'll measure it, and then once we know the amount of dissolved oxygen in the wine, we can kind of determine how we're going to treat it. And usually what we'll do is we'll sparge the wine with either nitrogen or CO2 to push out some of the oxygen. So, but the best thing is to just try not to pick it up in the first place. And then, of course, depending on the kind of wine we're making, if we're making like a sparkling wine or an aromatic white, they tend to have higher CO2, and so we need to make sure that before we bottle, that wine is in the range that we have identified as appropriate for the wine style. have a flame AA, and so this is an atomic absorption spectrometer, and we use this to measure copper. And copper can be added to wine to mitigate like off aroma molecules. So if we have some really stinky wine that maybe have like H2S or something in it, we can add copper to it, and copper will bind with the stinky molecules and actually pull them out of solution. And then we'll it's called racking, where we remove the wine off of the solids that have settled to the bottom, and so then at that point most of the copper and all of the stinky stuff's been removed from the wine. So this is kind of cool. It has a burner in it, and it's plumbed into an acetylene gas tank. And so basically what happens is we'll turn this on, the flame comes on, and we have a copper cathode lamp here. And so you can imagine the flame going, and the copper cathode lamp is emitting a wavelength into the flame, and the sample is like here, and this tube goes into the sample. Behind this little black piece here, there's a ball. It's called a nebulizer, and it basically like turns the sample spray into like, it thins it out to like where it's like an atomic what's the word, like density or thickness. It like spreads it out, basically spreads out the sample so that it's a super thin spray, and then it gets emitted up into the flame, and you can actually see the flame change color once the sample's been introduced to it. And what happens is once that's in the flame, it's being atomized, so it's being broken down into its atomic components, and the light from the lamp is absorbed by each type of atom in the sample, and the copper that's in the sample absorbs the light and then emits like a corresponding wavelength that is received by the detector, and that through like Beer's law is converted into concentration.
So you know about Beer's law?
Mm-hmm.
Our teacher was asking if we would ask you about that.
Oh yeah, this is, I mean, most of the spectroscopy is based on Beer's law, whether you're talking about the FTIR or the atomic absorber. Yeah, it's all pretty much uses that calculation, because you're taking basically a wave number, a wavelength, and converting it into concentration. So that's how that works. It's all a lot more interesting when it's working.
Yeah.
But you can use your imagination, I guess.
So all this is the process of fermentation, like the steps?
Well, yeah, fermentation and just processing steps. Yeah, so post-fermentation, wine processing. But yeah, typically we like to add copper during fermentation because the yeast holes that we add, or the yeast also binds with copper, and so it's really good at extracting it from the wine once it's done its thing. So, and that helps us because there are legal limits to how much copper you can have in your wine, and so the California law is like 0.5 ppm, so we don't want any more than that in our wine. And so, but we may add more than that, and then once it's done its thing and it's been pulled out by the wine holes, but even though we've added like say 0.5, it drops down to like below 0.1 ppm. So
what does the copper do to the wine? Like that makes it like, why would they make it illegal if it's over 0.5?
So copper is considered a a toxin in high quantities. So in higher concentrations, it can be toxic. Just like most metals, you don't want to ingest them in high quantities. But we're adding it at such low quantities that it's not a health hazard at all. In fact, the wines that we make have typically lower concentrations of copper in them than most city wines. So, yeah, it's very safe. But you don't want to, ingest large amounts of it. It's called a critical control point, and it's something that's regulated very heavily by, there's several, would you mind turning your radio? It's regulated throughout the state and the country, and any facility that's doing, food processing, wine processing. So we have all kinds of systems in place to make sure that we're tracking exactly how much is added, that we test the wine before and after, and that before we bottle it, we test it again to make sure that we know exactly how much residual copper's in the wine. And all of that paperwork is reviewed by multiple levels of management and regulatory bodies. So yeah, it's a very important kind of food safety aspect of wine processing. So let's see here. We have, let me grab a sample here. It's easier to explain when I actually have something. So this is called a turbidimeter, and basically it measures the turbidity of a wine, which is an indicator as to how much solids are in the wine. And before we bottle, we filter wines multiple times through progressively finer filters. We start with very rough filters, and then most of our wine goes through a sterile filter right before it goes into a bottle. But this number basically tells us how much solids are in the wine, and how long it will take to filter it. A wine that's been filtered and is bottle ready is typically below 1 NTU. So the units we're looking at are NTUs, and that's totally a wine unit. It's not something that you're going to run into in chemistry anywhere else, I'm pretty sure. But yeah, it's basically turbidity units. And so depending on, you can kind of tell what processing phase the wine's at based on how turbid it is. So neither one of these have been cross-flowed, which means that they are probably a ways off from being bottled. And they've probably just been combined and done a blend or something. They're just getting a sense of how long it's going to take for them to cross-flow, essentially.
Is any of this process different from red to white wines, or?
In terms of filtration,
yeah.
or yes, yeah. So white wines typically, they all go through the same basic steps. Cross-flowing is a large filter that pulls out most of the solids, pretty much all of the solids. And solids, are typically comprised of remaining yeast holes. Maybe there's some proteins or something in the wine. Maybe there's some turbidity that's contributed from aging it in oak, things like that. It's a combination of different things. So depending on how that wine was aged, depending on whether it was red or white, is going to determine what kind of processing and what kind of filtration it needs to undergo to become bottle ready. Here, so you guys asked about acidity earlier, and I told you that tartaric acid's the main contributor to the pH in the wine. It's really, there's a lot of different types of acid in wine, but tartaric is the most significant, I'd say. And tartaric acid is something that naturally occurs in wine. It's a process of the ripening of the berries, and but it's also something that's added to the wine. pH in wine is incredibly important to quality. So the typical range for wine pH is around 3.4. Maybe up to 3.7. 3.8 is getting a little high. Some reds are around 3.8. Occasionally you'll run into some like Bordeaux from Washington or France that's like closer to 4. They're less common, but they're out there. But that's typically considered a pretty unsafe range. The reason being that the less acidic the wine, the more hospitable the wine is to microbial growth. So you can have things like lactobacillus or Enococcus or Brettanomyces, which is a yeast that, you know, if there's a little bit of sugar in the wine and the pH is just high enough, they'll go off like that. That's their jam, you know, they're like, yeah, this is great, we love it. So we want to keep the pH low, but we can't keep it too low because then the wine's not drinkable.
Yeah.
So it's really a very tight range that we are targeting. Hey, Cindy. Hey. And we do that through a few things, but really making sure that our TA is on target is a contributing factor to that. So we measure TA and pH all throughout fermentation and processing. It's a really important quality marker. And this is an auto titrator. So just like our FTIR auto sampler, we can program samples in, load them up, and all we have to do is label the samples according to the positions that we're assigning, and we can scan the labels on the samples, which is great, and then just hit start, and this thing just takes care of it for us, and then we have it set up to where it automatically uploads data to our database. So we're eliminating manual entry of numbers, transcription, and that's basically eliminating transcription errors and, you know, just all of the little errors that you can make when you're actually manually writing down data. Try to eliminate that as much as possible. So yeah, so it's all pretty well automated, which is wonderful. And we just calibrate it every day and make sure that, you know, we're running controls with every sample, and our controls is this OXO wine here that's been, we have like a certificate of analysis for it that's run internally, and it's been validated with all of these instruments, and so we get basically this is an older one, but basically it gives us the breakdown of you know, alcohol, and then the range, anything that we would run on this wine. It gives us the breakdown, the instrument that it was run on, and the standard deviation that we are looking at. So that's how we make sure that we are keeping track of all of our instruments and whether they're on target and performing properly.
And that's all collected on the computer and then printed out for you?
Mm-hmm. Yeah. Well, you can see this here. So this was the last run that we did today, and this is one sample here. We have a pH measurement of 3.65, a TA of 0.55 grams per 100 mils, and then we ran the control. We call it the LCS, which is a laboratory control standard, OXO wine. And we've got our readings here, and then we ran one at the end and got our readings here. pH-TA looks like it dropped. It went up just a little bit, but it's still within range. So, and we do that with all of our instruments. We run controls at each end and then within certain intervals to make sure that let's say our instrument starts to malfunction halfway through a run. Well, instead of having to scrap the entire run, if we can verify that the controls were in within specifications between this end and this end, then we know that portion of the run was good. And then we might have to rerun another portion, but it can save us some time, so. Centrifuge, incubator. Not much to talk about there. So this is our only like real wet chemistry station here, and we use what's called Ripper method. So method developed by some guy named something Ripper, I guess. I don't know. To measure free and total sulfur. So just like TA and pH, free and total sulfur are like really important quality markers in wine. Sulfur is added to wine for a variety of reasons. Typically we'll add a little bit before we crush the grapes to kill off any wild yeast that might be in the wine or any bacteria. So basically sulfur is used as an antibacteria or antimicrobial. It's a preservative, and it's also an antioxidant. So we'll add it at various phases throughout wine processing, including pre-fermentation. So we're always going to want to know what the sulfur content is in the wine, and if we need to adjust it, add more for the aging process, to keep it from spoiling, all those kinds of things. So it's not very glamorous, but it's effective and it's fast. There's different methods to measuring sulfur. This one just happens to be kind of the fastest. It's not necessarily the most accurate because we're relying on manual titration. And so anytime you're doing manual titration and you're actually, physically measuring, it's going to vary from person to person. And so you have a large component of human error, essentially, in this method. But it's fast, and there's drawbacks. There's pros and cons to each kind of method out there. So the winemakers here they're okay.